Contours and edge detection are two of the key fundamental techniques in computer vision, and in this video, we're going to cover just that. Let's dig in. Hi, my name is Chris, and welcome back to my OpenCV in C# series. This series is meant to introduce and give you all the tools that you need to use OpenCV to its fullest extent, as well as some foundational building blocks to your computer vision journey. In this video, as mentioned, we're going to talk about edge detection and contours, which are both very large topics, but I'll try to break it down for you. We're going to cover three important functions and talk a little bit about the computer vision ideas behind them and the information you need to use them effectively, i.e. being able to tune them to get the best effect. If that sounds good to you, well, let's get started. So, what exactly do we mean by an edge on an image? Intuitively, you pretty much know what we mean, but if you think about it a little bit, what we're talking about is a significant difference between two areas in an image, some kind of distance between the values of two sets of pixels, right? Well, turns out it's much harder in practice, but luckily, some mathematicians figured out a few ways we can do it. The first we're going to talk about is applying what's known as a Sobel operator through convolution to our image. The important thing to note about Sobel operation on an image is that you're using a kernel, just like we did in the last video, which is convolved on the image, and that's giving you an approximation of the derivative of the image. Usually, this is done once for vertical changes and then once for horizontal changes, and then these two outputs can be combined together and give you a pretty good edge detected image. Let's see what that looks like. All right, so let's talk about Sobel. The first thing I'm going to need you to do is grab the next image we're going to use. You can use any image you want really, but I feel like we need one that gives us a more defined object to look at. Starry Night has a lot of edges to it. The resulting matrices that would come out of these operations would look pretty noisy. But this one, I got this cute little doggo here, and it's a pretty well-defined, especially on this side, you get a pretty well-defined edge here. You're going from pixels that are almost turned off to pixels that are fully turned on. The back side is a little less defined, but with a good edge detection, we'll be able to get that too. So as always, these pictures are in the GitHub repository if you'd like to download them and use the exact same ones. Or you can use your own and just experiment with it. You may need to use different threshold values, things like that, but we'll look at that in a second. So first, let's, as always, as is tradition, let's create a mat. And actually, we'll just do this. No need to instantiate, so we're going to do imread, and this one's going to be img dog. Okay, so now we've got our pick. The next thing to know about a lot of these edge detection functions is that they usually, at the very least, you want to do some noise reduction to for the algorithm to function better. So in our case, we're going to do that with a Gaussian blur, pretty standard. So I'm just going to create a new mat called that. And we're going to create a few other mats just to kind of give us something to work with and some examples. So the first one I'm going to make is called Sobel X. The next one is going to be Sobel Y. And if you were paying attention to the intro, you might be able to guess what the next one is. It's Sobel XY. And this is going to give us, we're going to have three examples of this Sobel function and the kernels that are used. The X kernel looks different than the Y kernel, and they both give you sort of a different version of the image, and when combined, give you a really good edge detection. So we'll print all three out so we can use those as example. And the next thing I'm going to do, I think I need to copy this to our guys. Okay. All right. And so now we're going to do our Gaussian blur, just like we've done before. And that input is pick Gaussian blur. A new system running out of size. We're going to do a 3x3 kernel. and then a sigma, which, let's see, we'll just do, for now, we'll do a 5. Okay. Sorry, what is it? Oh, comma. All right. So now we've got our Gaussian blurred image. So now we just need to do the Sobel function. And as you might have guessed, that is another CV invoke. And it's going to take these parameters. So there's input ray, which is, we're going to use our Gaussian blurred image. There's the output destination, which for this first one, we're going to do Sobel X. And then there's a depth type. We're just going to use the default type. That is an CV enum structure called depth type. We're going to use default. And then these next parameters are kind of what decides what type of Sobel you're doing. So this first one is X order. So we want to turn that on. So we're going to give it a 1. Y order, since we're doing Sobel X here, we just want to do a 0 there because we don't want to see the Y order on this. And then we're going to do a K size. That is, again, our kernel size. The default is 3. You can do pretty much what you want. I'm going to throw in 5 just to see what kind of effect we get. And then we're going to do the same function for Y and XY. So let me change this. And so the difference between X and Y, obviously we're going to use a different map. And then we're going to turn this bit off, this bit on. And for Sobel XY, we're going to do the same thing, except we're going to have them both on. Okay, so we've done our Sobel functions on our 3 images we want to show. Now we need to just show them. All right, so Y there and Y there. And then of course, as always, we need our wait key. All right, let's run this. Okay, so as you can see, there's some interesting stuff going on here. So Sobel X, important to note here, when you look at this image, it looks like you see a bunch of verticalness to it, right? And for instance, if you look at Sobel Y, you see a lot of horizontal to it. If you think about it a little bit, it makes some sense because your Sobel X function is giving you differences across the x-axis. So those differences are going to appear as lines that go up and down, right? So here, actually, if we look at the original picture real quick, you can see there's this vertical difference here, right? And so if you're going across the x-axis, you hit an edge there. This is why the Sobel X defines an edge there, but the Sobel Y do not, because going vertically, there's not much of a difference in those pixels. So hopefully that makes some amount of sense. You see a pretty well-defined edge around our dog on both of them. And then this is the Sobel XY. So when you combine both, outputs, you get places where there is a distinct change going kind of both directions, essentially. So you notice there's a pretty strong edge here, a pretty strong edge here, and so that edge shows up here. Our edge here does not show up because it's not that strong on the Y, Sobel Y. So as you can see, Sobel XY pretty good at edge detection among an object. So you could use this image to kind of if you wanted to extract this object out, you could do some math on the values of this image here and kind of extract that out. So that's pretty much how Sobel's used. Let's move on to another edge detection function called Canny Edge Detection. Canny Edge Detection was created in the late 80s by a man named John Canny. And really what he did was come up with a 5-step process that leads to a well-defined edge on an image once you get the parameters right. If you'd like to know more about exactly what that algorithm looks like, I'd actually recommend reading the Canny Edge Detector Wikipedia page because it lays out all the information in a very nice way and kind of takes you through the math. It's a good explanation. But for our purposes, we actually just need to know how OpenCV implements it. So let's look at that. And luckily, it's actually pretty easy. It's basically just one function call. All right, so we've already got some of the fundamentals we need, which is basically a Gaussian blur. That Gaussian blur image is going to be our input. Let's go ahead. I'll just comment this out so we don't show that and we can focus on Canny. So the first thing we're going to do, we're going to create a mat. We'll just call it Canny Pick. Okay. And then let's see. So probably the best way to start is with invoke.canny. So you can see the parameters here. There's an input array, there's an output array, there's a threshold 1, a threshold 2, an aperture size, and a L2 gradient. We're going to ignore the L2 gradient pretty much for now. The rest of them, let's talk through them. So the input is going to be our Gaussian blur. The output, we're going to do Canny Pick. And then, so these thresholds. Thresholds are basically what's going to determine how it defines the edges. It's going to take the lower of the two amounts and it's going to use that for one side of the function, and it's going to take the upper of the two amounts and use that for another part of the algorithm. So there's, you can set these manually and we can show what that does. There's also a way to calculate these automatically, basically. And let me show you exactly how we might do that. So, and this is kind of just for our purposes here today. You don't necessarily need to do this, but I want to show this because I think it's actually a pretty handy tool. Okay, and so the way we're going to calculate automatically our threshold values is we're going to actually calculate the average value of our image as a grayscale image first. So the way we're going to do that is with to image, and then we need a gray structure, which I believe, is from using emgu.cv.structure. Okay. I keep not being in BIM mode. So I believe we just needed that. Yep. All right. And so we're going to do a byte. And then, so that gives us our image as a gray byte tuple. And then we're going to do a function on that called getAverage. And what that's going to do is going to iterate through the image, and it's going to produce the average value of this grayscale image. And the reason we're doing that is because we're going to use that to calculate the lower threshold and the upper threshold. So the way we're going to do that is we're going to do the max of, this is for the lower, of 0 or 1 minus 3,3. I'll explain that 3,3 in a minute, times average dot intensity. And then for upper threshold, it's sort of similar, but except instead of 0, we're going to do 255, and instead of subtracting, we're going to add 0.33. Okay, so let me explain this a little bit. So actually, I found this on a Stack Overflow post. It's a kind of a nifty way you can calculate a decent, probably the best results you're going to get for your Canny Edge Detection. And what we're doing is we're taking the average of the grayscale image. We are taking the max of either 0 for the lower or 1 minus 0.33, which is a value, it's a sigma, and it was basically determined at some point with some math that that's the value you want to use. That's kind of that's what, for instance, a learning algorithm would converge to. And then we're going to multiply that by the average intensity. So whichever is higher of these two, and then the reverse for this. So all right, we're going to do lower threshold, upper threshold, and then we have this aperture size value. It has to be an odd value, usually I think it's between 3 and 9 if I'm not mistaken, but that aperture size is going to basically determine how much stuff gets picked up in our edge detection. If you turn it up, if you experiment with it a little bit and you turn it up, you'll start to see edges on places where the human eye definitely is not seeing edges. So It's almost like an intensity kind of thing. We're just gonna stick with the default of 3 for now, and we're gonna call it there. So, okay. So now in Canny Pick, we've got our Canny Edge. So let's show it. We'll just call it Canny. Okay, and let's run that. Okay, so this is what Canny gives you. It gives you extremely well-defined edges, though you will notice part of the animal is missing. The threshold values we chose pretty much ended up there. There wasn't enough difference to get through some part of the algorithm of Canny on that backside. So front side, very obvious edges. Remember this color is white on the original picture. This is darker, so very obvious edges there. Not enough on the back end. This is where you would play with your thresholds a bit. Try to get to where you can kind of do that. You may also need to do other processing on the image as well. For one thing you could do would be to play with your Gaussian blur, increase the intensity of it, decrease the intensity of it, because that's going to affect how edges are determined as well. You could also brighten the image. You could do a lot of things to kind of hone this in. For right now, I think we'll just leave it there because that's basically the basics of Canny. As you can see, it's a pretty cool effect. You really do get very distinct edges, and you could see how that would be useful in some cases. So, but for right now, we're going to leave Canny right there, and we're going to move on to contours. First thing to do would be to get the new image we're going to use for contours. I found this image. It is of an iPhone, and the nice thing about this is it has very distinct contours. It's also got inner contours here. As we'll explain in a moment, there's a hierarchy to contours, and it's got obviously the inner apple, things like that. So very nice image for displaying contours and doing effects with it. So that's the image we're going to use for this part. So the first thing we're going to need is, well, our iPhone, and we're just going to do read. Okay, and then the next thing we're going to need is a data structure to store our contour information. There's one specifically for that, and basically what this is going to be, it's going to be a sequence of points that then OpenCV can take in and, for instance, draw the contours. But it's how the find contour function will store the data given back to us, and that will be from a data structure called vector of point. And yeah, it's basically kind of how it sounds. It's a wrapper in Emgu for the vector of point data structure from OpenCV, and it will store our contour information. So and then from there's a few more things we're going to need. We're going to need a threshold pick. I'll explain what that is in a moment. And then we're also going to need a hierarchy. And again, we'll explain what that is in a moment. So first thing we need, we actually need a grayscale image of the iPhone. And so I'm going to do image gray white, and we'll call this gray phone. Okay. And then from there, we have pretty much all we need to determine our threshold image. So threshold is going to be a binary image, meaning every pixel is either turned on or off. And it's going to kind of use some logic that's in this function to turn on certain bits, turn off other bits. Duh. Makes sense. So let's invoke that and you'll see what I mean. So it's the threshold function. So we're going to do gray phone, and then, threshold pick. And then we've got some threshold values, threshold and max value. I tweaked these numbers a little bit when I was playing with this stuff. You're just going to trust me on these numbers for the effect we want, but obviously these are parameters you could tweak as you play with this stuff. And then this last one is a threshold type. Threshold type, let me show you what those are. It's a CV and num, and there's a few different ones. There's 2.0, which is one I've used before, binary, which is the one we're going to use. It's basically just saying which type of threshold you want. And so in this case, we just want binary. And then from there, actually, let's just show what this gives us. Okay, so this will give us our threshold image. All right, so yeah, pretty much as you can tell, it's basically if a specific pixel is over a certain value, it will turn it on. If it is under a certain value, it will turn it off. In our case, since our iPhone is white, that's going to be usually the ones that are turned on. You can see some light reflection pixels in here, which is what those are. That's why they're turned on, because that light reflection met some threshold value, or 210. And you can also see the shadow here. There's a slight curve or a shadow to the picture down here. And so the threshold, it didn't meet that value. So this is a pretty clean image. It's about as clean as we're going to get just for this image without doing more processing on the front end. So yeah, that's our threshold image. So what can we do with that? Well, there's a CV invoke function called find contours, and its parameters are threshold pick. So we give it our threshold pick, our contours, and then we also give it a hierarchy mat, which is where it's going to store the hierarchy information. To explain that a little bit, if you think about contours and how they work, so an object can have, depending on what type of structure you want, it can have a tree of contours, right? So obviously in this iPhone, this is the outermost contour. I think that one's pretty obvious. Then there's inner ones too. So a child of that contour would be this one, right? And this one. And then the children of those contours would be this one, maybe this one, depending on your values. There's none in here, so this has no children. But you can see how it would build a hierarchical structure with contours. And so that's exactly what we want it to do. And it's going to store that hierarchy information in this matrix. And then from there, there's also a retrieval type. And in our case, we want it to give us everything, basically. And so we're going to do a retrieval type enum, and it's going to be of type tree. You can also get the information as a list, and it explains what these do on this tooltip here. But in our case, we want a tree. And then the last value is a chain approximation method. This is actually basically just how do you want the function to work? And in our case, that is again a CV enum and of chain approximation method. And there's a few different ones we can use. In our case, we're going to use chain approximation none. And as it says, translate all points from the chain code into points. Easy enough. There's other ones too. This one is actually just straight up a different algorithm. But it's listed in there, and you can do that as well. But we're going to use chain approximation none. Okay, so this will give us our contours. And if we ran this and then inspected what was in this structure here, you're going to see basically a bunch of points, and those points in a sequence, and that sequence would be used to link. If those sequences of points were linked together, you'd get your contours. So I guess let's start with drawing the contours, just to kind of show that. So there's a function called draw contours, as you might imagine. And we're going to draw them on our iPhone, and we're going to pass contours. This contour IDX is a value you can pass. In our case, we're going to pass it -1, and that just means give me everything. There's the other values you can pass. I believe you can basically change the structure that you're sent back. MCV scalar color. So this is how the contours are going to be drawn, what color they're going to be drawn with. So we're just going to do a new MCV scalar, and let's do green. Remember, this is BGR, so green is the second byte. And then this last value is a thickness. We're going to do 2. Okay. So now if I'm show our iPhone again with contours this time. All right, so now we will see our threshold pick and our iPhone pick. Okay, so you can see it drew a green line where our contours are. So yeah, pretty cool algorithm. It gave us our hierarchical structure. Like I said, this is a child of this, which is a child of this, etc. So now that we have that information, let's actually use that information to then color inside of our contours. So the way we would do that would be cvinvoke.fillPoly, as in fill polygon, and the values we're going to pass are our input image. It's an input output image, so whatever you pass there is going to be the input, and also is where the output's going to be stored. We're going to pass it our contours, which is our input array of points. We're going to pass it a new MCV scalar, and in our case, we'll just do a nice blue, and then that will fill in our contours with our color. So we run it here, and we see a blue iPhone. The contour lines are still drawn on it. Without it, it may look a little more natural. I will say it did miss this area here, and that's because on our threshold pick, that area is missed. You could tweak that a little bit, and you could get rid of these light values out here and get rid of that, and you could, have a little more defined color. But hey, we just painted an iPhone, so. All right, in this video, I gave you some more of the fundamentals that you need on your computer vision journey, but what comes next? Well, next, we're going to talk about a tool that can help you solve some interesting problems and has some very cool applications. It's called template matching. So, lots of exciting stuff to come with OpenCV. If you'd like to see more of this type of content, please leave a like and subscribe, and let's get right into the next topic, template matching.